We're in our very last section, which is section 13.1. Many fast food restaurants use automatic soft drink dispensing machines that fill cups once an order is placed at a drive-thru window. A regional manager for a fast food chain wants to determine if the machines in his region are dispensing the same amount of product. He samples 4 different machines and measures a random sample of 16-ounce drinks from each machine. Do the data indicate that the mean amount dispensed from the machines is not the same? Use an alpha equals 0.05 level of significance. So notice that we are comparing 4 different machines. Anytime you're comparing 3 or more population means, you have to use the ANOVA test. So that's what we're going to do for this question. So we'll start by writing our hypotheses. So the null hypothesis will always be that the means are equal. In this case, it's going to be that all 4 means are equal. So mu1 equals mu2 equals mu3 equals mu4. And then the alternative will always be at least one population mean is different from the others. So very similar to the homogeneity of proportions hypotheses. At least one population mean is different from the others. So to do the ANOVA test, we first have to enter the data into lists. Because we have sample data from 4 different populations, you do have to use 4 different lists. I've already typed these into the calculator just to save a little bit of time. So you might want to pause and type them in. So you'll see that in this calculator, I've used list 1, 2, 3, and all the way up to list 4. So all the sample data from the 4 populations go into 4 separate lists. Now we need to go to the ANOVA test. So we go to Stat, arrow over to Tests. ANOVA is the very last one. So if you press the up arrow, there it is, ANOVA, and then press Enter. So now you need to tell your calculator how many lists that you used. It doesn't know until you tell it. So I'm going to put L1, comma, L2, comma, L3, comma, L4. Make sure you don't leave one out because that will really change your p-value. So I made sure I put all 4 lists separated by commas, and then you press Enter. And it gives you a bunch of stuff. This is the F-test statistic. F stands for Fisher. We don't really need that though. All we really wanted was this p-value here. So let's go ahead and write it down, and we're going to round it to 3 places. P is approximately equal to 0.004. I rounded up because of the 9 here. Okay, so then it says, do you reject H naught? Well, this is a very low p-value. It certainly is less than our level of significance, alpha equals 0.05. So because p is less than alpha, the answer is yes. We do reject H naught. Our results are considered statistically significant. So now we can go ahead and write a conclusion. I'm going to go ahead and restate what they say here in the question. So there is sufficient evidence. There is sufficient evidence to conclude that the mean amount dispensed from the machines is not the same. So I'm restating their question in a way. Dispensed from the machines is not the same, which was the alternative hypothesis. Okay, so let's try another one. The World Championship Pumpkin Chunkin' Contest is held every fall in Millsboro, Delaware. Contestants build devices meant to hurl 8 to 10-pound pumpkins across a field. One class of entry is the air cannon, which must use compressed air to fire a pumpkin. The following data represent a simple random sample of distances that pumpkins traveled in feet for years 2004 through 2007. Is there evidence to conclude that the mean distance that a pumpkin travels is different for the various years? Use an alpha equals 0.05 level of significance. Okay, so we're going to have to type these in the calculator, but let's write our hypotheses first. So once again, there are 1, 2, 3, 4 different samples here that have been obtained from 4 populations. So H naught will be mu 1 equals mu 2 equals mu 3 equals mu 4. There will not always be 4 for ANOVA, but there will be 3 or more. So 3 or higher, and you use ANOVA. If there was only 2, you could do a 2-sample t-test, right? But here we have 4. H1 is the same. At least one population mean is different from the others. At least one population mean is different from the others. Okay, so now we're going to type these data into lists. So stat, edit. I'm going to go ahead and clear out what I have here because I think my previous lists were longer than this. So I'm going to clear out all this stuff from my list. L2, clear, enter. L1, clear, enter. Okay, so let's type these in. 4224, enter. 4065.6, 3967.95, 3596.09, 3970, 3877.68. So those were the data values for 2004. Now 2005, 4331.72, 3633.79, 4267.49, 4237.9, 4211.17, 3034.77. Now 2006, 3870.5, 3579.43, 3623.65, 3275.19, 3022.24, 3632.59. All right, very last sample, 2007, 3489.85, 3416.15, 4211.27, 3238.09, 3579.62, 3552.72. Okay, hope I didn't make a mistake. A lot of numbers. All right, so now we can go ahead and run our ANOVA test. ANOVA, which stands for Analysis of Variance, does use the variances to find this p-value. Okay, so let's go up. ANOVA. I want to reference all 4 lists. So second L1, comma, second L2, comma, second L3, comma, second L4. Okay, and we press enter. And there it is. We have our p-value. It's about 0.074. So let's go ahead and write that down in the notes. P is approximately equal to 0.074. Our level of significance alpha up here was 0.05, so this was slightly higher, which means that our results are not statistically significant. So we do not reject H naught. Okay, this could just have occurred by chance, even if the means were equal. So let's go ahead and write our conclusion. I'm going to go ahead and use this portion of the sentence up here to help me write out my conclusion. So first of all, there is not sufficient evidence to conclude there is not sufficient evidence to conclude that the mean distance that a pumpkin travels, that the mean distance that a pumpkin travels, I'm stealing it from the sentence above, is different for the various years.